Okay, good morning, students. Let us start uh, the further things in the chapter Chemical Kinetics. We will try to complete the chapter almost 70% in this lecture. So, today we will learn about integrated 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 rate law equations. Okay, we will learn about integrated rate law equations. So this is very important, and many questions come from this part, from the part of the integrated rate law equations. So integrated rate law equation is an equation derived with the help of the rate law of that particular reaction. Okay. Okay, so first we will know about integrated rate law equation of a zero order reaction. First we will discuss about zero order reaction. You see, these are very important. The derivations are very important for board. Okay. Okay, let's start. Now let us consider a general reaction R2P, and let us consider that this reaction is a zero order reaction. Okay, we have considered a zero order reaction R2P. Now we know that d minus dr by dt, which means the rate of the equation, will be equals to, rate of the reaction will be equals to k r to the power n. Now we are speaking about zero order reaction, so this n value will become 0. So this will be 0. Now if this is 0, then further we can get minus dr dt equals to k into anything raised to the power 0 is 1. So k into 1 is 1. Okay, students. So now see, now we will take this dt to the other side of the equation. So we will get minus dr, very simple equation, very simple derivation. Now as you see, the term of dr comes, so if we need the value of r is the rate of r is the concentration of reactant, right? So in this integrated rate laws, our main aim is to find out the concentration of reactant at any time of that, any point of the reaction, at any point of time. Okay, so we will integrate both sides. After integrating both sides, we will get minus of r equals to k is constant, integration of dt will be t, plus this is a not a so that you will have a limit of, you will have a constant of integration. Okay, we will have a constant of integration here. Now for finding out this constant of integration, we will take this one, that take this condition. In t equals to 0, we have the concentration of r to be equals to r naught. Now r naught is the initial amount of reactant or initial concentration of reactant in this reaction. Okay. Okay, so we will put this one. So what will we get is minus r naught equals to c. So the value of c we get is minus r naught. Now let us come to this side. Now we will substitute. Now we will substitute the value of c in this equation. So what you will get is minus r equals to kt. Value of c is minus r naught. Okay. So if we bring this term this side, then you have r naught minus r equals to kt, equals to kt. Are you clear? We can make it a little more beautiful. We can write minus of kt plus r naught. Okay, so this is the integrated rate law equation for zero order reaction. Now you see, this r is the amount of reactant at any point of time. Okay, this r is the amount of reactant at any point of time. Now this equation is analogous to the equation of straight line. Y is equals to mx plus c, y is equals to mx plus c. So if we draw the graph, okay, if we draw the graph of concentration of reactant R versus T, you will have this way of graph, okay, and this is the intercept, so this will be R naught, so this is the graph of zero order reaction. Now see this equation very nicely. Okay, let us go a little more deep. You see, R to P we are speaking about, right? R naught is the initial concentration of reactant, and product concentration is 0. And now we are speaking that at any point of time, as the reaction proceeds further, the concentration of reactant is R. Okay, and whatever may be the concentration of product, that is a different matter. Now if R is the present amount of concentration, then there can be a question, amount or concentration of reactant reacted. That means how much concentration of reactant actually reacted. Okay, how will you find out this one? Concentration of reactant reacted, how much is the initial amount of concentration minus the concentration of reactant at any amount of time. Which is very evident from here. Value is kt. So kt will be the amount of the reactant reacted at any point of time, and the amount of reactant present at any point of time is R, which is minus kt plus R naught. That means R naught minus kt. Very simple. R naught is the initial concentration minus the amount of the reactant reacted in that amount of time. So this is all about the integrated rate law equation of zero order reaction. Note down all these things. Okay students, now let us come to the integrated rate law of first order reaction. Okay, these are very simple. Now first order reaction is very important. It is the most important part in this chapter. Okay, before going to that, let us see one more simple thing. That is, in case of zero order reaction, you have seen R naught minus R is equals to kt. Okay. Now we are speaking about a half-life period. We are speaking about half-life period. Half-life period. We are speaking about half-life period. Okay. So half-life period means what? Half-life period means what? The time in course of which the amount of the reactant which is left will be half of the initial concentration. That means, very simple mathematically, when R will become R naught by 2, when R will become R naught by 2, that time the time will be equals to T half, that is half life period. So for this we will put the value of R naught by 2 in this equation. Very simple. What we will put? R naught minus R naught by 2 is equals to KT. So this will be R naught by 2 is equals to KT. Therefore T half will be R naught by 2K. R naught by 2K. Now see students, in case of zero order reaction, we have got minus dr by dt is equals to K. That means the rate of the reaction is independent of the concentration of reactant and it is constant at any amount of time. It is constant at any amount of time, and the half-life period depends only on the initial amount of concentration. That means from here the relationship which we obtain, from here the relationship which we obtain is del dt is directly proportional to the R naught, and as the rate of the reaction is independent of concentration, so if we make the graph of rate versus concentration of reactant, this will be a straight line, and this value will be what? K. This will be a straight line, that means constant with the changing amount of reactant. So this is everything about the zero order reactions. Okay, now let us move to the first order reaction. First order reaction. Okay, now let us move to the integrated rate law of a first order reaction. Now this is very important. This first order reaction is very important. I will do only till first order. Second order is very simple. You can just do the simple integrations and can find out the integrated rate law of second order reaction. First order reaction is very important. Let us consider a reaction R2P. Suppose this reaction is a first order reaction. Okay students, now if it is first order reaction, then we can write minus dr by dt is K times of R raised to the power 1. We know this one very clearly. So ultimately if you take dt this side, this will be minus of R kr dt. Now you will bring the R this side, it will be k dt. We will be integrating both sides. The value of this integration will be minus log of R. Log means this is actually E base. Okay, we are speaking about the ln. The natural logarithm. Log base E, not the base 10. Okay. After that, t plus c. Now, for finding out the constant of integration, we will take at t is equals to 0. We will have the value of R is equals to R naught, right? Therefore, the value of C, we will substitute the value of C. Log of R is equals to KT plus what will be the value of C? Value of C will be minus log of R naught. Okay? Now let us come this side. If you bring this side, log of R naught minus log of R equals to KT. This is the thing equals to kt. Now you see students, log of a minus log of b will be log of a by b. So we can write it as log of r naught by r is equals to kt. Okay. Now you see, now r naught is the initial concentration of the reactant and r is the concentration of reactant at any point of time. So we need this one. So what will we do is, we can write r naught by r is equals to e की power minus kt. This is just simple formula of logarithm. If you want to remove this log sign, then this term, this term goes to the power of the base of the logarithm. Okay? So r naught by r will be this one. So if you want to get r will be r naught e की power minus kt. Now this is very very important formula. Okay? Very important formula. How it is very important formula, that you see that this R is the concentration of reactant at any amount of time. This R is the concentration of reactant at any amount of time. Okay? And this K is the rate constant and R naught is the initial rate. So in this case, if we plot the graph between the concentration of R and time, then this nature of graph become this way, exponentially decreasing graph. And if you increase this curve to cut the y-axis, cut the concentration axis, then you will get here obviously the value of r naught. Okay, so this is the final concentration versus time graph in case of first order reaction. Okay. Nextly, what we have to know is, we have to discuss little more deep things. As r equals to r naught e की power minus kt is the concentration of reactant present at any amount of time. Okay. Now in this reaction, what will be the, so r naught is the initial concentration of reactant, r is at any time. Now we are not going to the product. Now we are speaking about the amount of reactant reacted will be what? The initial amount of reactant minus the amount of reactant present at any amount of time. That will be r naught e की power minus kt. You can take r naught common, r naught 1 minus e की power minus kt. So this is the amount of the reactant reacted at any amount of time. Amount of the reactant reacted at any amount of time. Now last thing, let us find out the half-life of this first order reaction. For finding out half-life, we will replace this term with r naught by 2, r naught e की power minus kt. r naught can be cut. So ultimately it will be e की power kt. Equals to 2. Now we need this time. It will be half-life. You can just replace this by t half. So we will take logarithms on the both sides. If we take logarithm on the both sides, then this term will come here and log of e base e is 1. Okay. So just understand the mathematics. Suppose, just I am elaborating. If I am taking natural logarithm on the both sides, natural logarithm on the both sides, log of 2, this will be equals to what? K t half by natural logarithm of 2. Therefore, t half will be log base e2. Now see this formula very nicely. This is a constant quantity. So t half for a first order reaction is always constant. Depends only inversely on the value of the rate constant. But it is independent of the initial concentration or concentration of the reactant. Okay? So the half-life period, the half-life time in case of first order reaction is independent of the concentration of reactant. So this is the formula of half-life in case of first order reaction. Okay? So first order reaction is very important. Go through very nicely. There is everything about the first order reaction. Now just let us remember a short thing for this lecture. In general, T half is inversely proportional. You see, just in zero order reaction, you can see that the formula is R naught by 2K, and in first order reaction, the formula is log 2 by K. Log 2 by K. That's why we can write T half is inversely proportional to the R naught raised to the power n minus 1. This is the general formula. Now you see, just in case of zero order reaction, in case of first order reaction, if you put here 0, then R naught goes up, this satisfies. If you put here 1, this becomes 1. So independent of the concentration of reactant, this becomes right. So this is everything about the integrated rate laws. Go through very nicely, very important portions, and almost we have completed 70% of the syllabus of chemical kinetics. Thank you. Be safe. Jai Hind.